Hello, everyone. Hi, I hope you're all having a good day and excited for today, which is the second workshop of the Generative AI Educate Series with Boba Network. Today, we have a really interesting and exciting workshop by Gabor from Google Gemini, and he'll be giving a brief introduction to LLMs. So I hope you guys are excited for that. I'm just inviting him up on stage, and he'll be giving his workshop shortly. Hello.
Hello. Let's see if
Hi.
I can get the camera higher. Higher. No, excellent. Hello.
Perfect. Hello. Well, Gabor, whenever you're ready to share your screen and begin, the stage is all yours.
Sounds good. Thank you for the intro.
Of course.
Can you see my screen?
Yes, all looks perfect.
Excellent. So hi folks, my name is Gabor. I'm going to be talking to you a little bit about LLMs, a little bit of just brief intro, and a little bit of, practical tips and tricks. I'd be surprised if I have a full hour's worth of slides, so please ask questions. Please feel free to interrupt, and I'll be looking at the questions tab and maybe a little bit at the chat tab, and I'll try and get to it at natural stopping points just as I'm presenting. But if nothing else at the end, I'll try and go through everything. Also please post like what you're interested in. If there's like a particular topic that you want to go deeper in or less deep in, it's fairly fluid. But without further ado, so this is me. I started life as an academic. So I was a PhD student with Chris Manning back at Stanford. I actually went off to start my own startup, building chatbots for customer support, which was a fun and exciting experience that ended with an acquisition to Square, of all places, where we got to continue making a chatbot for customer support, but this time less for big enterprises and more for sort of the small businesses that operate on the Square payment platform. And recently, about a year ago, a little further, I joined Google, the Google Gemini team as an AI engineer. So what's this talk going to be about? I'm going to go over a little bit about just a background to AI and large language models, how these models train, how these models do inference, just at a very high level. And then I'll go through some of, well, I guess the progression of how to use a large language model, at least in my opinionated take, of starting with prompting, then applying fine-tuning, so sort of post-training to the LLMs, where prompting starts to become hard. And then I'll touch just a little bit at the end on how to do evals. It's much harder to write unit tests for a probabilistic system than it is for, a concrete piece of code. Awesome. So I'll start at the very beginning, just with a brief overview of like, what is programming? Well, if you're doing just a regular, Python program, you have inputs, you have some magic black box that takes these inputs and instructions, and they produce outputs. Your main method, taking text as input, text as output, what have you. Here we call the black box execution, and we call the instructions the program. When we go to machine learning, the fundamentals of it look similar. You have inputs, you have some black box that does stuff, it produces outputs, and there are instructions that tell it how to go from inputs to outputs. The big difference is that with machine learning, you're kind of doing a sort of meta programming. The instructions, instead of writing them yourselves, you have data and you have some architecture, some model architecture that go into another black box to produce these instructions. And first black box is called inference. So instead of, execution, it's inference. The second black box is training. You take data in your architecture, you train a model, which is your instructions that you use alongside your input to produce inference. Focusing a little bit on this section. What does training look like? Well, at a high level, you're trying to say, I want a model that maximizes the probability of my data. So the output is the model, the input is the data, and the whole training process is conditioned on the architecture that you've defined. Data is usually exemplars of inputs and outputs, so X and true Y. The architecture is a set of free parameters theta, so these are the model weights, a formulation of how you get an output from an input, so this is commonly the model architecture, and some loss function that says, hey, if I predicted something and this is the true output, then what should my penalty be? Did I do a good job or did I not do a good job? And then the model weights, the final model weights are just the values of the parameter theta after training finishes. So in math, this looks kind of like this. You're trying to minimize the sum loss over your data set of the actual predicted output given the model prediction, so given the formulation of how the model predicts something. And we started this with predict the data as well as you can. The predict part is this P of theta. The data is the summation that you're going over, and as well as you can is this minimization on the left-hand side. And this is the core, basically all machine learning, all supervised machine learning at least. LLMs are no exception. Here, the data is a partial sentence of the next word. So remember, data is input-output pairs x and y. We could have the input be the cat and then the output that we want from this is hat. And our job is to predict hat with as high a probability as possible. The architecture in this setting defines what is the probability of y given cat and the. So we go over all of the possible next words, or in practice subpieces, but you can consider them basically words for these purposes. It goes over all the possible words in your vocab and defines a probability of what is the chance that this next word comes after this prefix. The loss in turn is small when the model puts a high probability on the right word. So what we're trying to train the model to do is predict basically P theta hat given the cat and the with probability 1 based off this training example, and predict everything else with probability 0. The closer you get to that, the better the model performs. So if you ever see statements of the loss of this model goes down to 8 or whatever, that means that this probability is getting increasingly peaky. And all this is to say, a large language model is a next word predictor. This is just the fancy math behind what it means to be a next word predictor. Awesome. Within this paradigm, based on Dr. Seuss, exactly. I have 2 small kids, so there's a lot of Dr. Seuss in my life. Language model is next word predictor. Data tells you what to predict. Architecture determines how well the model predicts the data. Of course, it's important to have a lot of data. I'm sure you all hear about OpenAI consuming the whole internet. The more data it consumes, the more it knows, because the more suffixes it can predict. The architecture is, if you've heard of the transformer model. Speaking of small kids, not right now, Oliver. Thank you. The architecture is things like, if you've heard of the transformer model, that defines the architecture of the system, or the various GPT 1, 2, 3, 4, maybe soon 5, define variations of the architecture of how we're predicting this data. Kids always want screen time. I'm sure they'd be fascinated by the presentation. All right, let's focus on data. The architecture is actually in many ways the less important of the 2 of these. It's been transformers for the last, half decade or so at least, and mostly it's just small variations for this and that. The real magic behind large language models, both for your own applications and in many ways the pre-training, is the data that goes into them. Data is magical because it reflects the world. Optimally, it reflects the world as it is. So we can have, the professor lecture to her, and then there's a bunch of possible completions that you can have. Students is going to be the one that is written most about. And it's written most about because in reality, professors tend to lecture mostly to students, sometimes to friends, maybe in informal dinners or what have you, probably not to hands, and when is not even grammatical. And this is why AI works, because generally the text that we write down is in large part factual and reflects the world as it is. And therefore, if the language model picks up on all of this text as written, it's going to do a decent approximation of reflecting the world as it is. isn't 100% true. You could have, the professor lecture to her students about the dangers of, you have a bunch of options here. Arguably, rabies is a lot more dangerous than AI in the real world. It's, actually killing substantial amounts of people per year, but no one writes about it. And so the AI will, believe that that AI is going to be more dangerous, not necessarily because it's true, but because it's the thing that's most written about. You can extrapolate this fairly naturally to more insidious examples, but here is a less ethically hot topic one that we can illustrate it with. So beware, the AI doesn't actually know ground truth. It just sees what people have written and assumes that this is close enough to true for its purposes. All right, that is the first part. So that's the brief intro to LLMs and AI in general. I'll pause here in case people have questions before we go on to prompting and the later parts of the talk. How about bias in data for AI model training? Yes, exactly. That goes very much back to the data reflects the world as it's written. Part of this is also the data that is selected. Like, it is people that are choosing what makes it into these data sets and what does not. And there's going to be explicit and implicit biases in this. Again, some of the biases are good. For example, I think most of the big AI shops are putting a substantial emphasis on coding. Like, they're artificially subselecting more coding data to put into these AIs. As a consequence, the AIs become more useful at coding in particular, math more broadly, and it, as a weird side effect, it turns out the more code you put into the model, the better it becomes at reasoning, even in general, for some reason. Other biases, less good. Other times you're choosing to filter some type of data out, or you're choosing to overrepresent some type of data that, usually the engineers are well-intentioned about it one way or another, but it can go wrong. My favorite example, Gemini. I came from Gemini, and there's the big thing last year where the ImageN model started producing ethnically inaccurate images. You'd have like Black Abraham Lincoln or something, which, that was presumably a decision that was made about what data to include in the model. That was well-intentioned, but nonetheless led to the model not behaving in the world as it would or as the world is actually presented. If we go on to prompting, so there are two big knobs that you can turn with language models from like a practical perspective. Like, you're a developer, you want to go get started with something. Prompting and supervised fine-tuning. Prompting within the model of like what is a language model is just next word prediction. So you can have tell me a joke, and the model has been trained with a sufficient number of data sets that do this sort of instruction following that it knows that the next thing to generate after this is going to be a joke. Why? Because in the data set, there's been enough examples of tell me a joke, or something similar, that and having the next word be a joke, or like here's a joke, or what have you, that like it happens to do a pretty good job. If the question is why does it happen to do a pretty good job, that's a big mystery. I don't think anyone knows. A lot of people are fairly surprised that next word prediction works as well as it does, but it works very well, and it's very good at absorbing a large amount of data, a wide variety of data, and in practice, emulating intelligence quite well. All right, Gabor's mental model of prompting. So there's a common question of, at least that I get a lot of, like, when should you prompt? When should you do fine tuning? My mental model is that the pre-training set for these language models is so unfathomably large that almost all of the knowledge and capability that you can get into the system is already there in the pre-trained model. So if your model knows how to do something, you can get it to do it with prompting. The use case for fine-tuning is when the model does things 80% of the time, and then 20% it goes off the rails or does something surprising. Or when the model does something 80% right, but there's that 20% where it does something just a little bit wrong, or it has two choices that both seem very reasonable, but one is preferable to the other. Then you can teach it these little tweaks, this literal fine-tuning. via a fine-tuned model. And the common thing that I hear in response to this is, okay, but prompting isn't working. So what can we do to make it better? So this part of the talk is, I guess, Gabor's tips on prompting from things that I've seen work well and work poorly within Gemini, building products on top of the Gemini models. The first most common and probably most powerful one is chain of thought. So these are things like think step by step, or another common pattern is to tell it the meta plan of what you'd like it to do. First, think about doing this, then based off your response, do this, then finally do this. A third variant of this is self-critique. So where you tell it to go write an answer, like write a poem in the style of Dr. Seuss, and then in the same prompt you can say afterwards critique it, see how you can improve it, pay attention to these concrete criteria, and then write another answer below it. Why does this? And then there's a bunch of other variants that you can do with this, but generally, like the more tokens, the more thoughts you put into it, the better the model output will be. The extreme case of this, by the way, is things like the reasoning models. It's like the OpenAI 0, 1, 2, I guess 3 soon series of models, where they're literally under the hood, just having the model chat with itself. So it's just a whole bunch of chain of thought before it produces a final answer. But even without the reasoning models, you can get a close approximation to this, and you can often tune it particularly for the task that you want with these sorts of tricks. So why does this work? Partly it works because more tokens just lets the model literally think more. You have more, like every token that you consume is more computation that the model gets to do. The other reason that this works is it lets the model look ahead. So if we go back to how do language models work, it's always predicting just the next token. It never gets to look ahead to what is the next 3 tokens. Within this paradigm, it can often get stuck in some direction that it thought it was good when it started generating, but then turns out it's not as good halfway through. Like it has no real good way to proceed, but it kind of has to do it anyways. Chain of thought lets it, in part, foresee what happens next. So this is the think step by step, or the first think about approach. Or in the other case, it can look backwards and say, hey, this is what I generated. Now I actually see the whole thing. Did it go well or did it go poorly? Like maybe I should retry it. I'll wait for questions until the end of the prompting section, and I see a couple showing up. The other technique that you can use is start it off on the right track. So this is in the same vein of a language model can only see a little bit ahead. And the hardest decision it can make is what is the right, very first place to start. Which makes sense. Like the instructions naturally flow from each other. And then there's at some point a token that's like, all right, you're done with the instructions, go play. And that very first token is often the most uncertain of what is it exactly that the user wants? How should I actually start? So an easy way to solve that is to just tell it where to start. For example, if you're generating JSON and you're having trouble getting it to actually produce JSON, you can have it literally, start your response with open bracket. And it'll have a very easy time following that. And then once it starts with that, it will have a very easy time saying, okay, I'm in JSON mode, let me continue generating. Another common tactic that I use now and again is give it kind of a template of begin by writing, begin by writing something like, I need to blank in order to blank, fill in the blanks. And then the model will know that it has this structure that it needs to follow, and it'll literally fill in, almost template fill this, and then continue on doing smart stuff. The third tip that I'll put here is, one that's hard for me and maybe less hard for normal people, but I have a bad habit of trying to talk to the language model as if it were a computer. And over again, I learned that it's better if you talk to it as if it's a person. Imagine some contracted worker, or even your friend next door, and you're trying to tell them how to do this task. The more you're in that mental model, and the less you're in here are steps you have to follow, here's the program to execute, the better things tend to work. Related to this, shorter prompts, strangely, tend to be better than longer ones. Like often there's a temptation to just put more and more stuff into the prompt, and sometimes it works better, sometimes it actually just doesn't. Other little tricks, a common one is start with "you're an expert in blah, blah, blah." You're an expert travel planner, you're an expert chef, or whatever task you're trying to do. And then it gets the model into the right, almost humanish brain space of like, okay, this is my persona. Let me respond in this theme. Why does this work? Most of the data sets were written by non-engineers here. Like it's generally not programmers that are sitting down and writing the inputs and the outputs. In fact, when we've tried that, it leads to terrible results, not recommended. And so the more you match the language of the people that generated these data sets, the better the instruction following tends to go. And that is my last prompting slide. Let me go through some questions. How does the grammar syntax of natural language factor into model training? For example, can you remove stop words from your language data, but for it to be coherent response, you still need them? I actually don't know if there's been any experiments of training a language model explicitly removing stop words. I know there's a very old paper that shows that for sentiment classification, stop words actually end up being surprisingly important. This is very old, so not language models, but I think the insight might still be relevant, that there's more information in stop words than we think there is. The other side of this is, yes, you very much want to match the grammar and syntax of the training data when you're generating. So the better formed, the more grammatical your prompt is, the more likely it is that you'll get a good response. Just because the model will be in a more familiar space. It'll kind of have seen similar sentences in the training data and be able to generate similar sentences going out of it. In principle, so long as you match whatever's in the training data, it should work. It's like if you train a model on some different syntax, in the extreme case, if you train a model on a different language and then prompt it in a different language, then it'll work fine. If you train a model on a different language and then prompt it in English, for example, it'll just completely poop out, unless you've also trained it on English. The next one, if LLM is just predicting the next word, then how is it able to detect issues in code or come up with images based on text descriptions? That is a very good question. So for the code one, the image one is the easier one. The image one, usually there's a shared embedding that you have between the text and the image. So the process here is you consume the text, and then the internal state of all of these LLMs is going to just be a very large vector, a couple thousand element vector. When you're generating more text, you take this hidden state and you take all the hidden states in the prompt and use that to generate the next token. When you're generating an image, usually it's a somewhat different model for the actual image generation, but it takes as input that same hidden state that's meant to encode sort of the meaning of the sentence. And similarly to how you would do it with text, you generate an image, you compute a loss for how similar, how dissimilar is this image from what I was supposed to be generating, and then that can backpropagate into this hidden state and backpropagate into the encoder model to get it to generate better images. Code, the simple answer is there's nothing particularly magic. It just turns out that language models do a particularly, do a good job of learning syntax. There are a couple of insights in there that are relevant. One is that clearly it has some sort of counting. And this is true even before transformers, like even early language models, the LSTMs and similar architectures were able to do things like paren matching, which means that somewhere in this hidden state, this hidden vector, it knows that, I am 3 indents in, and I am in this function here, and so I need to continue writing this sort of thing. So that's one trick. The LLMs are able to have some sort of memory-ish behavior just stored within the weights. Also, why chain of thought works. It can sort of store things that you might not expect it to store in these thought tokens. The other answer that I can give is just that there's a ton of data about it. Like if you've encoded all of Stack Overflow and if you've encoded all of GitHub, and I know certainly OpenAI has done both, then like you've just seen most of these, and you can memorize fairly large chunks of code with fairly little variance. I guess the question was detecting issues in code. That one I think is more of a mystery. I think it's trained on the same sort of data. So like if you read the code and then you have an issue that you've pasted, it's doing the same sort of thing we're doing. It goes to Stack Overflow, finds the most similar cases, and then copy paste the answers to those. Though with a bunch of auxiliary data. Like I'd be surprised if basically everyone doesn't have a whole bunch of data on exactly this use case, just because it is such a common use case for users of LLMs. Going on for Adam, have you found that certain prompting techniques work better or worse with certain models? The more powerful models are much more sensitive to the prompt, is the only consistent trend I've found. So all these techniques should work for all the models. When you have a more powerful model, you can be shorter, but you have to be more precise. It's kind of the trade-off. Because if you give the wrong instruction to a more powerful model, it'll follow it, and it'll follow it incorrectly. Whereas less powerful models are, in some sense, more forgiving, but in other sense, dumber. Like they also just follow the instructions worse. And otherwise, most of the models are comparably powerful now. Like OpenAI is still, I think, marginally better than all the rest, but Claude is not far behind, and Gemini is, I think, also comparable to Claude, or if not, also not far behind. Prompting, zero-shot and few-shot prompting. Yes, I did not mention few-shot prompting in here. Oftentimes, putting in exemplars helps a lot. My own experience, I've tried one-shots. Well, I've tried zero-shots, one-shots, and few-shots. The sweet spot, I think, is one-shot. And really what I found works the best is one-shot where you kind of templatize the answer. Like if you're generating code, write out the pseudocode of roughly what you might want for a query, or write out a sketch of what you might want, and then the model kind of interpolates and infers from that. But I also have not experimented much with multi-shot training examples. And I do hear from others that it works well. Will Google produce projects feature to Gemini? Oh, this is the like OpenAI Cloud projects. No comment. I'm not here in an official Google capacity, so I should not comment on things that are not in the Google pipeline. Is there a level where pouring more tokens into the prompt doesn't get you much? What is this level number of tokens? In my experience, there is. So certainly, like I think there's a soft limit and a hard limit. The hard limit is when you go from short context to long context models. Long context models are just generally worse at attending to the whole prompt than short context models. The reason here is naively attention is quadratic. So the more tokens you have in your prompt, the runtime increases quadratically. There are tricks, of course, to make this not the case, because we can't have a 1 million by 1 million quadratic blow up for these long context models, but these are all necessarily approximate. So as soon as you go past whatever the backend has defined as the like short context versus long context limit, you get worse attention, so you get worse instruction following. The softer, I guess, advice that I can give is that if the instructions start being hard for a person to understand, it's probably hard for a model to understand too. Like if you read them and you have trouble keeping everything in your head, then not much more than that will start getting hard for the model to also keep it in its head. The second one is the lesser of the two effects, and the first one is the greater of the two. Gareth, I found that LLMs will give me an answer even when it doesn't actually know. Yeah, this is definitely a big research problem. I don't think there's any like single best practice solution for this. There are a couple of things that can mitigate it. One is incorporating external knowledge, like you can do, for example, a search call and then paste in the search results. and the model will do a better job of recognizing if the answer is or is not in these results. Another thing you can do is critique. So you can have the model generate something, and then you can just ask it, like, is this right or not? And sometimes that'll work okay. Asking the model explicitly to say if it doesn't know also sometimes works, though the challenge here is that these models aren't really trained on a semantic level. They're trained primarily on a syntactic level. So generating something, do I want a tattoo? I'll want a tattoo soon, okay? So that, like, they're not actually penalized all that much for generating incorrect data, so long as it sounds reasonable, so long as it sounds like something that's written. In conclusion, it's a hard problem. No super best practices other than the usual critique and revise and similar approaches. Awesome. So next section is going to be on fine tuning. So fine tuning is oh, there we go. We get an image. Fine tuning is when you go back to the training step, but you add in more data. So this is just like the training step we had before, but there's this pre-trained model that you feed into the fine-tuning process. This is the one that was trained on Xillion tokens and already does a decent job. And then what you're doing is you're just feeding in a little bit of extra data specific to your use case. What you get out is a bespoke model, and the hope is that if you use this bespoke model, then you do a better job of generating your particular outputs from your particular inputs. The danger of this, of course, is that if you've trained the model to do something very particular, it might forget how to do something very general. So almost always, when you fine-tune your models, you lose overall instruction following at least a little bit, which is a trade-off that you have to consider. Guidelines for SFT, similar to the prompting tricks. Clean data, like the most important one of all of these, clean data is much, much better than more data. The more data you add in part, the more likely it is for the model to forget what it already knows, just because you're putting in more stuff to distract it. And much more importantly, if you put in noisy data, if you put in data that's doing the wrong thing or doing something that's not warranted in the prompt, then you're actually just explicitly asking it to forget how to instruction follow. Like you're telling it, okay, this is what's in the prompt, this is what I want to generate. What I want to generate is not in the instructions, so just ignore the instructions and do this instead. Related insights, I guess by number, even a couple dozen fine-tuned examples should go a long way in teaching a well-prompted model how to behave well. And my general advice is, when it's not working well, first look through the data, even if you've looked through it 5 times already, and see if there are tweaks you can make, little fixes you can make that would explain why the model's not behaving well. And then only after that, try to add more data. In a similar vein, the second bit of advice is the more real the data is, the better it works. Engineers are very bad at the fine nuances of predicting what users are going to ask or what the real query stream is going to look like. The model is very good at picking up on these subtle differences. And so oftentimes, if there's this sort of skew of what you expect the model to look like and what people are actually using the model as, you'll get worse performance in practice than maybe even your eval sets say that you should. I touched on the third one a little bit already. Match the purely prompted output style as much as possible. The more the model, quote unquote, wants to generate the data that you're fine tuning on, the better it'll do, the less it'll forget. The last tip I have here is that negatives are really hard to encode. So you can do some stuff with SFT to like have it generate an empty set or something. In a little bit, Oliver. Can you go to mama? Oh, okay, we might get a kid joining soon. Negatives are hard unless you have something like reinforcement learning, which is a much more direct way to penalize the model doing something wrong. And in my experience at least, it's almost easier to handle negatives by using chain of thought self-critique type techniques than it is to try and encode negatives in supervised fine-tuning data. That is all I have for SFT. Any questions? Or the last section is going to be on just a tiny bit on evals and how to quote unquote unit test your language models. Well, so last section, evals. How well is my model working? This is true for both a fine-tuned model or just a purely prompted model. It's probably the hardest of the like practitioners' skills for dealing with language models, because models only as good as your eval. I mean, it's similar to programming, where okay, maybe I'm just a bad programmer, but my code never works unless I unit test it, and your code really only works as well as your unit test coverage is. Similarly, your LLM only really works as well as your eval set is useful. So how do you quote unquote unit test models? Well, step one, you collect an eval set. So this is similar to what your training set would be. Sorry, like your training set. That's a typo. But you only need the queries. You don't need the outputs. Similarly, the more like the actual query stream this is, or optimally, if this is an actual query stream, the better. Step two, write a rubric for what makes a response good or bad. And this is like the unit testing component of it. So you should have a good idea of what it is that you want the model to predict and be able to describe it coherently in something like a rubric, or at least like instructions for like, rate this from 1 to 5 based on these criteria. And then step three is throw this into an eval. If you have lots of money, have humans eval it. That's always going to give you the best output. But it gets expensive if every single run of your unit test, so to speak, you have to hire a bunch of people to evaluate your model. If you're on a tighter budget, startup style, then you can write an LLM prompt to do these evals. And the magic here is that this rubric is good both for people and for models. Like a language model does usually a pretty good job of following it, at least approximately. And if you have a medium amount of money and enough time to invest into proper evals, the best happy medium, in my opinion, is to do some human evals. For example, a lot at the beginning, and then just like every month or every couple of months, run another human eval set just to make sure that you're fresh. And then use the data that you get from these human evals to fine-tune an auto rater. And at this point, you get the best of both worlds. You get sort of the speed of an LLM, but you get something that is close to the accuracy of a human, just because you've trained the autorator on these human evals. So that is my one slide little summary on evals. There was a question from Adam. What do you mean by pure prompted output style? So this is the last. Thank you. This is the last slide. Where match purely prompted output style. What I mean here is that if you have a query and you have a prompted model, it's going to generate some text as output or some content as output. When you are collecting your training data, you want the output in the training data to be as similar to this output that the model would naturally predict as possible. And this is kind of fuzzy. Like this could mean that you run the prompted model and they just like clean it up where it messed up. This could just mean that you try to write your training data in, LLMs. Like they definitely have their own, particular tone when they're generating data usually. But the less surprised the model is by the training data it gets, the better tail patching or the better supervised fine-tuning tends to work. A question from Vlad: we can use LLMs to evaluate LLMs. How good is it? Moderately is maybe the answer I have. It is definitely good enough to be usable. It's usually very noisy on any particular example. like correlated but noisy enough that anything except the extreme cases, is not necessarily super informative. But over the course of a whole data set, so if you have on the order of hundreds of examples that you're evaluating every time, you can get the correlation actually be quite good. So you at least get signal for like, hey, I have two models or two prompts. I've run both over this training set, over this eval set, and the auto evals, the LLM evals, give me this model is substantially better than that model. You can usually trust that, even if you can't quite trust it for like, hey, on this example, the eval said that this model is better than that model, if that makes sense. These are good questions.
Hey, well, Gabor, thank you so much for that. Yes, of course. If people have more questions, please do put them in the question chat. We do have a little bit more time, but of course, Gabor, you have been answering throughout, so totally fine if Gabor has answered everyone's questions. But if you have any, now is your chance to ask them.
Yep. I'll be extra slow on this next question to give people time to add more. And indeed, it looks like we have some time to answer questions if folks have them. From Vlad again, LLM models for harmful response evaluation. There's another hot button topic. How do you do AI safety? Indeed, you can usually do a pretty decent job having an LLM be predicting whether content is safe or unsafe along different dimensions, especially if you know the dimensions that you want it to evaluate on. If you don't, you run the risk of the LLM making up its own criteria for what it should and shouldn't be doing. But similar to just general evals, if you have a good rubric for like, this is what the LLM should be doing, this is what the LLM should not be doing, you can usually get an LLM itself to be able to evaluate its own safety. That was not as long of an answer as I expected.
Don't worry. Any other questions? Totally fine if not. But there's another one.
How do we create SFT datasets from a collection of documents for fine-tuning the model? I see. So this would, if I understand the question correctly, this is something like a larger unsupervised training corpus. If you have a relatively large collection of documents, and then you want it to capture the knowledge and information that's in these documents. I'm actually not entirely sure what the APIs for this look like. Most of the time, at least when I've been using LLMs for fine tuning, I've been doing it for a particular task. So you have like a known input and a known output, and you want the model to be particularly good at generating the output from the input. But there is another type of post training, which is just putting in other types of documents. This is definitely possible with certainly like the raw APIs to LLMs. I don't know what's actually exposed in the public APIs. The trade-offs are relatively similar. Of the more new content you put in, the more risk there is of forgetting the old content. And this is particularly relevant when it's just background text, because you want it to learn the knowledge in the background text. But there's also usually more of this, and it's usually substantially more different from the stuff that it was pre-trained on. That the risks to pay attention to here are forgetting the core instruction following. I'm not sure that's a particularly satisfying answer. It's a thing that's done. It's possible. The risks and trade-offs are similar to other sorts of fine-tuning. Jailbreaking prompts. Why will some jailbreaking prompts work on some models and not on others? I'm trying to gauge how much I'm allowed to say on this without getting into trouble. The short answer is that I think every model has some mechanisms to avoid jailbreaking. And like these are the other note I'll put here is these are there for you. Like the main point here isn't to protect IP or something of the sort. The main point here is to prevent against the LLM equivalent of viruses. For example, having some bit of malicious instructions put into the prompt without you knowing. Like you read some, browse this website, and then summarize it. And if that website has like white text that tells the model to do something terrible, then potentially it can do actual harm. Especially as these LLMs start taking real actions in the world, start like being able to send emails on your behalf, or control your computer on your behalf. And so companies try to create a separation between sanctioned instructions, sort of what the system can do, and user space instructions. That is what you prompt the model with. And they try to not allow user space instructions to have the same permissions and do the same types of things as system-based instructions, like reading its own instructions, like modifying its own system instructions. The mechanisms that different companies do for this are going to be different, and different models sort of trying to handle this in different ways. And so the techniques to try and get around this are going to work for some models and work for others.
Great. Also, Ridwan has asked if you would mind sharing the link to the slides potentially, so that we can share that in the chat. That would be really, really helpful.
I can do that right now.
Thank you very much.
Actually, I can. Here are the slides.
Perfect. Does anyone have any other questions? Like I said, everything will be recorded and uploaded on our YouTube for tomorrow.
Awesome. Well, thank you all for. There's one more from Adam. If LLMs are trained on internet data, how much of it will be biased by the amount of things like hate speech, pornography, etc.? So this goes back to the filtering question and the biases, where oftentimes there are deliberate decisions made to exclude certain types of data sets from training the model, most of the time in order to generate a model that we more want to interact with. And like these are examples that are, I think, often filtered out. The other answer to this is safety. Like oftentimes these are post hoc filtered out, especially when you have an LLM that purportedly speaks authoritatively. It is dangerous and harmful if it is saying things that are not meant to be authoritative. Short answer, it's filtered out. Some of it I'm sure makes it in, and so we try to filter it out post hoc. How effective are these filters in your opinion? I should probably avoid opining too much about safety filters. I think they're not perfect. They're also not terrible. They do an okay job most of the time, with, of course, ways to get around them, and there's a continuous effort to try to improve them. At, again, basically any LLM provider I know, this is an ongoing and very high priority effort.
Amazing. Well, if anyone, if that's all the questions, like I said, this is recorded and it'll be uploaded on our YouTube tomorrow. Gabor, thank you so much for such an interesting and informative workshop, as well as answering all these really, really great questions. Thank you everyone as well for asking them. It was really, really good, and good to see all your engagement. If that is all the questions, then I'll say thank you, Gabor. Thank you everyone for tuning in, and I hope to see you guys next week for the next workshop in this Generative AI Educate series. And I hope everyone has a really great rest of their day. Thank you.
Thank you so much.
Thank you. Bye.